Noise in op-amps, in low noise in low noise applications, the input referred noise of op-amps becomes critical. We now extend the noise analysis of differential amplifiers in chapter 7 to more sophisticated topologies with many transistors in an op-amp. It may seem difficult to intuitively identify the dominant sources of noise. A simple rule for inspection is to mentally change the gate voltage of each transistor by a small amount and predict the effect at the output. Let us first consider the telescopic op-amp shown in figure. At relatively low frequencies, the cascode devices contribute negligible noise, leaving M1 minus M2 and M7 minus M8 as here you can see the figure noise in a telescopic op-amp. The primary noise sources, the input referred noise voltage per unit bandwidth is therefore similar to that in figure A and is given by Vn square bar equal to 4 kT into 2 into 2 by 3 gm12 plus 2 into 2 gm78 by 3 gm12 square plus 2 into kn by wl12 c0 xf plus 2 into kp by wl78 c0 xf into gm78 square by gm12 square, where kn and kp denote the 1 by f noise coefficients of NMOS and PMOS devices respectively. Hence, we study the noise behavior of the folded cascode op-amp in figure A, considering only thermal noise. At this point, again, the noise of the cascode devices is negligible at low frequencies, leaving M1 minus M2, M7 minus M8, and M9 minus M10 as potentially significant sources. Do both pairs M7 minus M8 and M9 minus M10 contribute noise? Using our simple rule, we can change the gate voltage of M7 by a small amount. Figure B. Nothing that the output in need. Here you can see in this figure noise in a folded cascode op-amp. Changes considerably. The same observation applies to M8 minus M10 as well. M8 minus M10 as well. To determine the input referred thermal noise, we first refer the noise of M7 minus M8 and M9 minus M10 to the output Vn out square bar M78 equal to 4 kT 2 by 3 gm78 square r square out, where the factor 2 accounts for uncorrelated noise for M7 and M8, and R out denotes the open loop output resistance of the op-amp. Similarly, Vn out square bar M98 is equals to 4 kT 2 by 3 gm9 and gm9 m9 square r out square. Dividing these quantities by gm12 square r out square and adding the contribution of m1 minus m2, we obtain the overall noise. Vn int square bar is equals to 8 kT into 2 by 3 gm12 plus 2 by 3 gm78 by gm12 square plus 2 by 3 gm910 by gm12 square. The effect of flicker noise can be included in a similar manner problem. Note that the folded cascode topology potentially suffers from greater noise than the telescopic counterpart. As observed in the differential amplifiers in chapter, the noise contribution of the PMOS and NMOS current sources increases in proportion to their transconductance. This trend results in a trade-off between output voltage swings and input referred noise for a given current as implied by Gm equal to ID by VGS minus VTH. If the overdrive voltage of the current sources is minimized to allow large swings, then their transconductance is maximized. As another case, we calculate the input referred thermal noise of the two-stage op-amp shown in figure. Beginning with the second stage, we note that the noise current of M5, here you can see in this figure, noise in a two-stage op-amp and M7 flows through R0 5 parallel to R0 7, dividing the resulting output noise voltage by the total gain GM 1 R0 1 parallel to R0 3 into GM 5 R0 5 parallel to R0 7, and doubling the power, we obtain the input referred contribution of M5 minus M8 M5 minus M8 V n square bar M5 minus M8 equal to into 4 KT 2 by 3 GM5 plus GM7 R0 5 parallel to R0 7 square into 1 by GM1 square R0 1 parallel to R0 3 square GM5 square R0 5 parallel to R0 7 whole square is equal to 16 KT by 3 GM5 plus GM7 by GM1 square GM5 square into R0 1 parallel to R0 3 whole square. The noise due to M1 minus M4 is simply equal to Vn square bar M1 minus 4 equal to 2 into 4 KT2 by 3 GM1 plus GM3 by GM1 square. It follows that Vn dot square bar equal to 16 KT by 3 1 by GM1 square into GM1 plus GM3 plus GM5 plus GM7 by GM5 square R0 1 parallel to R0 3 whole square. Note that the noise resulting from second stage is usually negligible because it is divided by the gain of the first stage when noise referred to the main input. Thank you.